All right, everybody. Well, good morning. I'm going to try to summarize the last 50 years or so of asteroid spectroscopy in about 20 minutes, so bear with me. Next slide. So reflective spectroscopy is a study of light that is reflected off the surface of an object. And the most widely used wavelength region to study asteroids is in the visible and the near infrared from about 0.4 to 2.5 microns. This is because this is where the sun emits most of its energy. Also, this wavelength region is very easy to observe from Earth because the atmosphere is relatively transparent. Also, really importantly, many minerals that are found in meteorites and therefore asteroids have characteristic absorption bands in this wavelength region. An absorption band is a wavelength location where light is absorbed rather than reflected. And in the example you can see here in the upper right-hand corner, there are two absorption bands, one at 1 micron and the other at 2 microns. Next slide. Olivine and pyroxene are the two most common minerals found in meteorites and asteroids. Olivine has 3 absorption bands near 1 micron that form a asymmetric 1 micron feature. You can see that's labeled band 1. Band 1 moves to higher wavelengths with increasing FeO content. Oops, you got ahead of me there, Mike. If you can go back, yeah, thank you. Then pyroxenes have 2 bands. They have a band at band 1 and at band 2, and both of these bands move to longer wavelengths, either as Fe2+ substitutes for Mg2+, or as Ca2+ substitutes for Fe2+. So if you have an FeO-free pyroxene, like instatite, for example, that would have a featureless flat spectra in the visible in the near infrared. So you would not see those absorption features. When we describe absorption bands, we usually describe them in terms of a band center, which is the center of the band, specific wavelength after the linear continuum is removed. Next slide, please. Band area is another useful spectral parameter. The area of each band is determined by drawing a straight line, as you can see here, from the tangent to the peaks on both sides of each band, so band 1 and band 2. And then we determine the area between the straight line and the spectrum. The band area ratio can be used to estimate olivine and pyroxene abundances in asteroids and meteorites, as first demonstrated by Clutis in 1986. Next. So a lot of work has been done to characterize the spectra of ordinary chondrites, and ordinary chondrites are the most abundant type of meteorite. They account for more than 87% of all meteorite finds. The ordinary chondrites, as you can see here, are divided into 3 different groups: the H's, the L's, and the LL's. These are categorized based on 2 things: iron nickel metal content and the FeO content of olivine and pyroxene. So the H chondrites, H stands for high, those are metal rich, so high metal, and they contain the most FeO poor olivine of all of the groups. The LL chondrites, they contain the lowest abundances of metal, but the highest FeO content in olivine. And then the L chondrites, of course, are intermediate between the H's and the LL's. The H and L chondrites make up 90% of all ordinary chondrites, and the LL chondrites are the remaining 10%. And this will be important later when we start looking for parents. So next slide, please. So the reflected spectra of meteorites can be measured in the laboratory and then directly compared to asteroid spectra. Samples are usually made into a powder, and then we remove metal because metal suppresses band depths. The earliest laboratory studies of meteorite spectra go back to the 1970s. One of the biggest was Gaffey, 1976, was actually part of his PhD dissertation. He measured the reflectance spectra of about 150 meteorites, and they represented most of the types of meteorites known at the time. If you look at the spectra here for the H's, the L's, and the LL's, you can see that there are some variations in the way that those spectra look, and that's a reflection of the compositional differences that I just mentioned, and I also have listed on the right-hand side here. So for example, if you look at the LL chondrites, those are the ones that have the highest abundance of olivine and also the most FeO-rich olivine. So band 1 and band 2 are at the highest wavelengths. And if you look at band 1, you'll see it's very asymmetric, and so that's most consistent with an actual olivine spectrum because it has so much olivine in it. The H chondrites, if you look at band 1, you'll see it's much more symmetric, and that's because pyroxene is absorbing more strongly in the H's and the L's. Next slide. So because spectral parameters like band center and band area ratio are affected by composition, we can use them to derive calibrations for determining mineralogy of asteroids. These surfaces have been revised, these formulas have been revised over the years. like I mentioned previously, the first was Clutis, 1986. They developed a formula for determining olivine and pyroxene ratios from band area ratio. We still use revised versions of this formula today. Some other examples, just kind of in between, in 2002, Gaffey devised formulas for determining pyroxene compositions. And I've got some data here, or some formulas here from Dunn et al. It's actually Dunn et al. 2009, not 2010. I clearly can't remember when I've written things. In this paper, myself and colleagues, we developed formulas for deriving the composition of olivine, pyroxene, and also abundances of olivine and pyroxene. This was done using actual ordinary chondrite spectra or ordinary chondrite mineralogies, which was new at the time because most of these previous studies had been based on mixtures and not actual ordinary chondrites. And if you look at the figure on the right-hand side, that's the data from that study. So the H's, the L's, and the LLs in their compositional regions. And we showed that we can correctly classify more than 80% of ordinary chondrites and S-type asteroids using those formulas. So next slide. Oops, excuse me. So for more than 50 years, the search for the parent bodies of the ordinary chondrites has centered on the S-type or the X-complex asteroids. S-type asteroids have moderately steep reddish slopes. You can see I've highlighted those in red here on this slide. And they also have absorption features at 1 and 2 microns. So they have spectra that are very similar to the ordinary chondrites. S-type asteroids are also the most common asteroid in the inner main belt, accounting for about 40%. You might also notice if you look towards the bottom here that Q-type asteroids also have spectra that are consistent with ordinary chondrites. However, those are not very common in the asteroid belt. Next slide. So comparisons between ordinary chondrites and S-type asteroids have been complicated over the years by the fact that the spectra of S-type asteroids are redder and they have shallower bands than the ordinary chondrites. And so that's made it very difficult to make a definitive link between the two. So laboratory studies suggested that this was probably due to space weathering, and we've heard a lot about space weathering today and also yesterday as well. And so what you're looking at here on the right-hand side, this is just one example. This is a study from Sasaki et al. 2001. What they did was they took olivine pellets and they irradiated them with a pulse laser, and that was to mimic high-velocity micrometeorite impacts. And so they showed that the olivine spectra gets redder as they are irradiated for longer periods of time. So what you're seeing in the figure here, the bottom line, the solid line, that's the original olivine pellet. And then as you move up towards the top and the lines get more dashed, those have been more irradiated. So this is just one example illustrating that space weathering can certainly cause the reddening that we see in the S-types. However, that was very difficult to know for sure without a space mission. Next slide. So in 2005, the Hayabusa spacecraft collected material from asteroid Itokawa, as we all know. Itokawa was thought to be an LL chondrite based on ground-based reflected spectra, and you can see that on the left-hand side. When we got samples of Itokawa back to the lab and analyzed them, we were able to determine that Itokawa was indeed an LL chondrite. And if you look at the figure here on the right-hand side, this is showing phaolite composition in olivine and ferrocylite in pyroxene of the H's, the L's, and the LLs. And Itokawa here, which is the little blue diamond, plots very firmly in the LL chondrite region. So it does have an LL chondrite mineralogy. An examination of individual grains revealed the presence of microcraters and sulfur-bearing nanoparticles. And so all of these observations confirmed that the reddening of the S-type asteroids was in fact the result of space weathering. This also helped us to understand that the Q-type asteroids are unweathered ordinary chondrites. Next slide. So the best way to search for parent bodies of asteroids or parent bodies of ordinary chondrites is to look at the surface mineralogies of the S-type asteroids. And so the first study to do that was Gaffey et al. 1993. They determined the mineralogies of 32 S-types using band area ratio and band 1 center, and observed that they basically represent a nearly continuous mixing line from pure olivine to pure pyroxene. And so you can see olivine, pure olivine is up here in the top left-hand side, labeled OL, and then the pure pyroxene is down here at the bottom right, labeled OPX. And so you can see the combinations along the way. Next. So they developed a classification scheme for the S-type asteroids based on these spectral parameters and divided the S-types into 7 subtype classifications. And so we have S1 through S7. So S1, those are our olivine-rich asteroids. S7, those are the pyroxene-rich asteroids. And then they suggested that the S4 classification, which is this polygon shape here, has mineralogies that are consistent with the ordinary chondrites. And in the insert, you can see, this is again some data from Dunn et al. 2009 of showing LLs, L and H chondrite compositions, and they do, of course, plot in that specific area there. So they suggested that would be where we should look for sources of the ordinary chondrites. Gaffey also observed that many of the S4 asteroids were near the 3-to-1 resonance, and so they suggested that might explain why so many ordinary chondrites make their way to Earth. Next slide. So even before space weathering confirmed the link between the S-types and the ordinary chondrites, researchers began searching the S-type asteroid population for possible sources of the H's, the L's, and the LLs. And the first identification was made by Gaffey and Gilbert in 1998. They suggested that asteroid 6 Hebe was the parent body of the H chondrites. This was made primarily based on the spectral parameters of Hebe. Its band 1 center, its band area ratio were consistent with the H's, and also the fact that it was located near that 3-to-1 resonance with which Gaffey suggested was important for getting those samples to Earth. A couple other lines of evidence that were helpful in this particular classification was the bulk density of Hebe, which is consistent with the bulk density of the H chondrites, is very close. And then Baki et al. 2010 found that the distribution of cosmic ray exposure ages of the H chondrites was consistent with derivation from Hebe. Next slide, please. So in 2008, Vernaza et al. Compared the spectra of 38 S and Q-type near-Earth asteroids to a database of ordinary chondrites, and they applied a radiative transfer model to analyze and compare those mineralogies. And what they discovered was that the majority, in fact, 2/3 of near-Earth asteroids have LL-like compositions. And so you can see that illustrated well on this diagram on the left-hand side. The top is a frequency distribution for ordinary chondrites, again showing that the majority of ordinary chondrites are H's and L's. And then right below that in black, that's the distribution or the frequency for the S and the Q-type near-Earth asteroids. And you can see here, the frequency is primarily in the LL region. So that was surprising. Why would we have so many LL-like asteroids when the majority of ordinary chondrites are H's and L's? Vernaza suggested that this might mean that kilometer-sized near-Earth asteroids, which are the ones that we are typically observing telescopically, are not the direct parent bodies of most meteorites, and instead those are meter-sized objects, and we'll talk a little bit more about that a little bit later. But then what Vernaza also did in this study was they decided to look specifically at the Flora family, and the Flora family is an important family in the inner belt. It accounts for 15 to 20% of asteroids, and it also borders the B6 resonance. And so they suggested, based on location and composition and abundance, that the Flora family was the parent or the source for the LL chondrites. Next slide. So searching for the L chondrite parent body, I think, is really interesting because we have a lot of constraints on what that asteroid must have looked like. We know that the L chondrites or the L chondrite parent body must have experienced a catastrophic breakup about 470 million years ago. That's based on argon-argon dating of shocked L chondrites. This also coincides with the stratigraphic age of fossil L chondrites that are located in Ordovician sediments. The cosmic ray exposure ages of those fossil L chondrites indicates a very rapid delivery time, 1 to 2 million years. So the parent must also be close to a resonance that can deliver material very quickly. And then finally, we know that slow cooling rates of the L chondrite parent body suggest that it had to be greater than 100 kilometers in diameter. So we have some really good constraints on that particular parent body. So in a 2009 study, Nesforni et al. Examined basically all existing asteroid families greater than 2.5 AU. And they suggested that only the 5-2 resonance was capable of transporting meteorites to Earth on timescales that were comparable to those CRE ages. There are only two S-type families that are near the 5-2 resonance. That's the Gefion family and the Coronis family. The Coronis family, however, we believe is too old to be the source of the L chondrites. And so Nisforni focused in on the Gefion family. They identified all of the members in that family, as you can see in this diagram, and the colors and the shapes are basically sizes of objects. After they cataloged all of the samples, they did a size frequency distribution and estimated the size of the Gefion parent to be 100 to 150 kilometers, which is consistent with the size of the L chondrites. And they estimated a formation age of 485 million years plus or minus 40. So the age is also consistent. So they suggested that the Gefion family is the source of the Ls. Next slide.
You have 5 minutes, Tasha.
Excellent, thanks. So since the NS40 study in 2009, the catalog of the Gefion family has been updated, and the new size frequency distribution suggests that it's older than 500 million years. And so that appears to be too old to be the source of the L chondrites. So in a very recent study, this is just this past fall, Marcet et al. Conducted a new spectroscopic study of all S-type families in the main belt. They basically used a radiative transfer model to determine mineral abundances of all of these families and confirm the compositions of families as determined in previous studies. So like, for example, the Flora family and the L chondrites. But there were two big exceptions to this, and that was the Massalia family and the Phocaea family, which I'm probably saying incorrectly. But the Massalia family is the important one here. If you look at the composition of Massalia, what we had previously used to determine the composition of that family was the largest asteroid, and that has a composition of an H chondrite, as shown here in the gray. But you'll notice that all of the other samples or bodies in that family that they looked at in the study actually have compositions of L chondrites. And so they also basically looked at all of the chondrites or all of the near Earth objects in the inner belt and saw that the majority of L chondrites are right around the 3-to-1 resonance, which again could get material to Earth relatively quickly. And those L chondrites also have an inclination of 1.4 degrees, which is important because there's also a zodiacal dust band at the same inclination. So using size frequency distribution models, they determined an age of 450 million years and also suggested there was a second disruption or impact event 40 million years ago, which was responsible for the zodiacal dust band. And so they suggested that Massalia is the source of the Ls. Next slide. And then in another very recent study, Braz et al. Suggested that modern collisional events in the asteroid belt are the primary source for the most of the meteorite flux to Earth. They look specifically at the H chondrites because we know that 40% of H chondrites have young cosmic ray exposure ages, so between 5 to 8 million years, which would indicate a relatively recent breakup of the H chondrite parent body. So they examined young S-type families in the main belt and identified 3 clusters, or 2 clusters primarily, the Coronis 2 family and the Charon family. And Coronis 2 is the bright pink, Charon is a dark purple. Those 2 families have orbits, I should say, that converge on ages that are consistent with those cosmic ray exposure ages. So Coronis is 7.6 million years and Charon is 5.8. Both of these also have the same inclination as the Iris dust band, which is at 2.1, and that can be associated with the breakup event of those 2 families. And modeling in the study also suggested that both the Charon and the Coronis 2 family can produce a substantial number of meter-sized bodies. And remember now, our understanding is meter-sized bodies are the direct source of meteorite flux to Earth. And they can both produce more meteoroids than even the largest families. And so they suggested the H chondrites are from the Coronis family and also confirmed that the Flora family is the source of the LLs and the Massalia family is the source of the Ls. Next slide. So I will just leave the summary right there, and I might have a little bit of time for a question or two, or you can feel free to type something in the chat and I'll respond to that for you. Thank you.